All right, let's spark things up today and dive deep into something electrifying, electricity. We're tackling potential difference today.
It's a big one. Really key to understanding how all the tech we use every day actually works.
Exactly. And we've got this super cool interactive simulation from, get this, Open Educational Resources, Open Source Physics at Singapore. Their website is awesome.
They're doing some really great work to make physics more accessible, fun for everyone.
For real. So, get this. You're in this virtual lab and can build your own circuits. Drag and drop stuff like batteries, bulbs, you name it. But here's the
There's
twist.
always a twist, right?
Always. You have to build a water circuit first before you can even touch the electrical stuff.
Ah, that's clever. They're using the classic water circuit analogy.
Yeah, to help wrap our heads around this whole potential difference thing. It's pretty abstract.
Analogies are super powerful for learning. Connecting something new to something we already understand makes it way easier to grasp.
Makes sense. So walk me through this water circuit thing. What's it all about?
Okay, picture this. You've got a water pump pushing water through pipes. The pump, that's like the battery in an electrical circuit.
Providing the juice, the energy.
Yep. And those pipes are like the wires. The water flowing through them, well, that represents the flow of electrons. That's what we call electric current.
Okay, so I kind of see the connection here, but where does potential difference fit into all this water stuff?
All right, imagine two tanks of water. One's up high, and the other's way down low. The water's going to flow from the high one to the low one, right?
Gravity's going to do its thing.
Exactly. That difference in height between the two tanks, that's like potential difference in an electrical circuit. Measured in volts, it's like the pressure that pushes those electrons through the circuit.
So the higher the water wants to fall, the more energy it has to push through those pipes.
Exactly. In an electrical circuit, that translates to more energy to power a bulb or make a motor spin, whatever it's hooked up to.
So the simulation, it actually shows you this connection between the water circuit and the electrical circuit.
It does. When you build the water circuit right, boom,
Yeah.
the electrical circuit pops up, almost like it's being powered by that water flow.
I bet if you mess up the water circuit, the electrical one vanishes too, huh?
You got it. It's a cool visual way to reinforce that potential difference is a must-have for electricity to flow. Just like water needs that height difference. No pressure, no flow, right?
Right. But let's be real for a sec. The water thing is a great starting point, but potential difference in an electrical circuit, it's ultimately about the difference in electrical potential energy between 2 points, not just about physical height.
Absolutely. We have to remember that. Think of it like this.
Yeah.
Electrons, those tiny particles zipping around in the wires, they're attracted to points with lower potential energy, like a ball rolling downhill.
Makes sense. The bigger the energy difference, the stronger the pull.
Right. And the more those electrons are motivated to move, the more current you get.
So, just thinking out loud here, the type of wire would also affect things, wouldn't it? Not just potential difference. Some materials conduct electricity better than others.
You're totally right. That's resistance. Think of it like a narrow pipe restricting water flow, even with a big height difference.
So potential difference is like the driving force, the push, but the wire's resistance is like a bottleneck.
A great way to think about it. And the interplay between those two, potential difference and resistance, that's what determines how a circuit behaves. It's where things get really interesting.
All right, I'm hooked. Let's unpack this relationship more. But first, let's zoom in on how this push of potential difference actually affects different parts of a circuit. What does it really do to those components?
Yeah, let's get into the nitty-gritty of how potential difference makes things happen.
Okay, so we've got this awesome water circuit analogy to help us understand how voltage, that potential difference, acts like a push for electrons. But
Wow.
how does that push actually show up in a real circuit? Like, what does it actually do?
Well, think about that light bulb in this simulation. The brightness of that bulb, that's directly related to the potential difference across it.
So you're telling me if we crank up the voltage, the bulb gets brighter.
Exactly. The greater the potential difference, the more energy that little bulb gets. And the more energy, the brighter it glows. It's like cranking up the pressure in a water circuit, making that water wheel spin faster.
Gotcha. So that's one way potential difference affects things. But what about other components? Does it influence anything else besides light bulbs?
Oh, absolutely. Potential difference, it's like the maestro of the circuit. It dictates how all sorts of elements behave. Take a motor, for instance. The speed at which it spins, totally dependent on the potential difference applied to it.
So higher voltage, faster spin. Makes sense.
Like pushing a merry-go-round. The harder you push, the faster it spins. But it's not just about making things brighter or faster. Potential difference also dictates how much energy a device uses.
Oh, so like my electricity bill.
Yep, exactly that. The power a device consumes, directly tied to the voltage. That's why we use high-voltage power lines to transmit electricity over long distances. Minimizes those energy losses.
So there's a reason those power lines are way up there. It's not just for the view.
Nope. It's all about efficiency. And speaking of, this brings us to another important concept, voltage drop.
Okay, voltage drop. Lay it on me. What's that all about?
Let's go back to the water circuit for a sec. As the water flows downhill, it loses some of its energy, right, due to friction and stuff.
Makes sense.
Same deal in an electrical circuit. As those electrons flow through, they lose a bit of their energy as they pass through each component. That energy loss, that's voltage drop.
So the voltage isn't disappearing, it's being used up.
Bingo. And that voltage drop across a component, it's a measure of how much energy that component is using.
Interesting. So let's say we've got our simple circuit with a battery, wire, and that trusty light bulb. There's a voltage drop across each of those things, right? Does the amount of voltage drop tell us anything about the component itself?
Oh, for sure. The amount of voltage drop across a component, it's linked to its resistance. Components with higher resistance, like a super long, thin wire, they'll have a bigger voltage drop than something with low resistance, like a short, thick wire.
So it's all connected. The potential difference, the resistance, the voltage drop. It's a balancing act between these factors that determines how much current flows and how much energy gets used.
Exactly. And that's the key to understanding how any electrical circuit works. Doesn't matter if it's simple, like our simulation, or complex, like the circuitry in your phone.
This is making me see potential difference everywhere. It's not just some boring concept in a textbook. It's the engine behind all the electrical marvels around us.
Couldn't have said it better myself.
Yeah.
The more you explore it, the more you realize how fundamental it is to our modern world.
So let's step back for a minute and think big picture. We've talked about how potential difference affects those light bulbs, motors, and how much energy devices guzzle up. But where else does this show up in the real world? Any surprising examples out there?
Well, have you ever thought about how nerves send signals in our bodies?
Now that you mention it, it is electrical, right?
Exactly. It all boils down to potential difference again. Our nervous system uses electrical signals, and guess what? Those signals happen because of differences in electrical potential across cell membranes.
So it's not just about powering our gadgets, it's part of how our own bodies work, too. Mind-blowing. Makes you realize how fundamental this potential difference thing really is. What other natural systems rely on this?
Well, how about electric fish? Some of them can generate electric fields around themselves.
Wait, really? They have like built-in batteries?
Kind of. They have spiralized organs that create differences in electrical potential, just like in our circuits. And they use these electric fields for all sorts of things. Some can stun their prey with electric shocks. Imagine that.
Wow, so potential difference isn't just about lights and motors, it's a weapon too. Nature is amazing.
It is. Some electric fish even use these electric fields to navigate, communicate, or sense objects around them. It's like having built-in radar.
That's incredible. Potential difference is way more than just circuits and wires, it's everywhere. I was just thinking maybe we could even explain something like weather patterns using potential difference.
Like areas of high and low pressure creating winds and storms. That's an interesting thought. You know, meteorologists do use the term pressure gradient, which describes the difference in atmospheric pressure between 2 points. And that pressure gradient, that's what drives the movement of air, creating those winds and weather patterns.
So maybe it's not exactly the same as electrical potential difference, but it's a similar idea, right? A difference in energy driving a flow. I'm telling you, the more we talk about this, the more I see potential difference in everything.
It's amazing, right?
Yeah.
That's what physics is all about.
Yeah.
Finding those core principles that connect things that seem totally different. Potential difference is a perfect example of a concept that pops up everywhere, even in places you'd never expect.
I think we've really shed some light on potential difference today. Not just how it works in circuits, but also its role in nature and beyond. We've covered electric fish, weather patterns, and even how our own nervous systems use it.
It's been a fun ride exploring all these different facets of potential difference.
Yeah, it has. So to our listeners, we challenge you to keep those brains buzzing. Check out that simulation we mentioned, the links in the show notes, and see what other connections you can make with potential difference.
The world is full of surprises. Who knows, maybe by understanding potential difference, we can understand even more complex systems and figure out new ways to solve problems.
And that's a wrap for today's deep dive. We'll catch you next time. Keep that curiosity alive and keep exploring.
Always keep learning.